your screen right now. Yeah.
Yeah.
Thank you.
Okay. Thank you. Thank the organizers very much for the opportunity to give a talk here. So I will talk about his pair production at NQL. This work is based on the this talk is based on the works with Longbing, Huashen, and Jian. Okay. For the motivation and introduction, as we know, his potential plays a very important role in the standard model, and his self-coupling is a very crucial parameter for his potential and electroweak symmetry breaking. So here is the equation for the Higgs potential. In the potential, we have two parameters, mu and lambda, the Higgs self-coupling. So the lambda Sm in the standard model, it is equals to Higgs mass square over 2 times wave square. It's around 0.13. So the shape of the Higgs potential is defined by the mu and the lambda here. The shape of the potential directly connected to the phase transition of early universe, for example. And there are so many new phase models related to the Higgs sector, so which can change the Higgs self-coupling or Higgs coupling to other particles. So in the standard, if we want to measure the Higgs self-coupling, we can study this for different channels. For example, gluon fusion to Higgs pair, so vector boson fusion to Higgs pair, and the double Higgs production associated with a vector boson or associated with a TD bar. And the relevant cross-section can be seen in this plot. As you can see, the gluon fusion to Higgs pair has the largest cross-section, and the current prediction is at the NNNLO with a FT approximation for the total quark mass effect. And the VBF has a second largest cross-section, and then TD bar HH and the VHH and so on for the single top associated with Higgs pair, for example. So in this talk, I will focus on the gluon fusion to Higgs pair production. So for Higgs pair production in the standard model, the tree level, the Bourne level diagram is like this one. So it's reduced by a top quark loop. And it is very difficult to study the loop-induced cross-section, especially for the massive quark in the loops. And a way to perform the high-order QCD calculations is to integrate out the top quark loop. Then we will have an effective theory. So, for example, here we have an effective coupling between the Higgs and gluon, two Higgs and gluon, one Higgs and gluon. So at the Bourne level, as you can see, these two diagrams will contribute to differently. They depend differently with the self-coupling. So at the leading order, the cross-section will be proportional to this term 1 minus something times his self-coupling. So if we can measure the total cross-section for pair production, then we can directly translate the uncertainty of the cross-section to the uncertainty of the self-coupling. So this is a direct measurement for the Higgs self-coupling. For the effective Lagrangian, it can be written as in this way. So we have a Higgs pair interact with a gluon field. Yeah, we can also expand this equation to 3 Higgs, 4 Higgs, but for Higgs pair production, it's enough for us to study this. CH and CHH are the Wilson coefficients. So they are known up to 4 loop analytically. So if we work in the effect theory, we want to study the high order QCD corrections. We have to deal with two kind of a diagram. For example, the first one is there's only one effective vortex. As you can see, the Higgs directly can interact with the gluon, and we have a single Higgs produced and decay into double Higgs. For this kind of a diagram, the amplitude can be written as a coefficient. So pair Wilson coefficient minus Higgs production, single Higgs production and decay factors in times of gluon structure function. For the gluon structure function, it has been calculated up to 3 loops. And another class of diagram is like this one. So it is has 2 effective vertices and up to n cube LO, we need to deal with 1 loop and 2 loop calculations for this kind of a diagram. And for all the 2 loop matrix element, you can find the matrix element in this paper in 2018. And also in their paper, they call this kind of a diagram as a class A and a class B contribution. So similarly to the amplitude, we can classify the matrix element square into 3 different channels. So for example, if the matrix element square has 2 effective vertices, we call this as a class A, and 3 for class B, and 4 for class C. And the total cross section will be sum of the class A, B, C. So as shown here in these figures. And as we know, each effective vertex associated with at least 1 alpha S. Then for class A, it's really an cube LO corrections. For class B, it will be something similar to the NNLO cross section. And for class C, we need to deal with the 1 loop correction, so it's NL correction. So the situation is summarized in this table. So I will come back to a similar point later. So what we will use is the QT slicing method. So it is it's well known, well used for NL calculations. And the cross section is divided by 2 parts. The first part is a pair PT smaller than PT veto. Second part is a pair PT larger than PT veto. So if we want to calculate the NNL corrections, we only need the NL corrections for this part for the Higgs pair plus jet, and for the smaller than PT veto cross section, we can use TMD factorization to calculate it. So the factorization can be written in this form: hard function convolution with a beam function and solve function. The only channel dependence component here is the hard function. So we have A, B, C, the definition of the hard functions. For the beam function or TMD PDF, the solve functions, they are process independent. And for now, we have the 3 loop gluon beam function and the solve functions. And if we can perform the Higgs pair plus jet NNL calculations differentially, then it's possible to calculate the class A cross section up to n cube LO, but currently we didn't find any public code to calculate the Higgs pair plus jet NNL cross sections. So for class A, we have to use another way to deal with this problem. Okay, so before I show you class A, so for class A, we reproduce all the NNL corrections. As you can see, the smaller than veto part, larger than veto part, and combine them together, we have an independent, we have the cross section independent on the PT veto. For class A, we will use a different approach to calculate the cross section. For example, we can divide the Feynman diagram for the Higgs pair production into 2 different parts. First part is gluon to 1 Higgs, and second part is 1 Higgs to 2 Higgs decay. So for the 2 Higgs directly coupled to the gluon field, we can also separate the contributions. Then the cross section of class A can be written as a phase space factor times an matrix element ratio for the single Higgs and double Higgs production times a Higgs single Higgs cross section with the replacement of the Higgs mass to pair environments. So for the second part, for the last part, we know it up to n cube LO. For the second part, we can expand it order by order in alpha S. In the end, we can get n cube LO corrections for the pair environments distribution. So here is what we can do for possible cross-check. First of all, we can reproduce the full NNLO corrections for Higgs pair production. And then second, for n cube L corrections, For class C, because it's effectively NL correction, we can compare with metal graph 5. For class B, we can use a QT subtraction to calculate the NL corrections. For class A, as I showed you in the last slides, we use a single Higgs production and cross-section and do an alpha S expansion there. And for the NLO cross-sections, we can compare with the literature here, and we can use I-Higgs 2 plus metal graph 5 for class B, I-Higgs 2 for class A, and we can also in total use a QT subtraction to calculate the cross-section. As you can see, they are the 3 different methods they agree with each other very well. For different classes, the contribution is different. As we know, the class B is one order higher in alpha S than class A, so the cross-section is about a percent level corrections to class A. And also for class C, so one order alpha S higher than class B, the cross-section is even smaller. So here is the total cross-section, and the total cross-section depends on the square root alpha S. As we know, for the Gruen initial state processes, the QCD cross-section is very large. So NLO corrections are around 87%. NNLO is 18%. For the A cube LO, what we found is increase the total cross-section by 3%, but the scale uncertainty here is less than 3%, as you can see here. And what we can get the differential cross-sections is the Higgs pair environment mass distribution. So this is exact at the N cube LO. As you can see, this from leading order, next leading order to N cube LO, we can find a very good probability of convergence. And scale uncertainty are reduced significantly. The ratio between the N cube LO and the NNNLO, so it is showing this band here, it is almost flat. So the conclusion is similar for the 100 TeV collider. So for the Higgs pair production, we have to think about the total quark mass corrections. So for the total quark mass corrections, we can studied in the full theory. Currently, only NLO cross-section is available. Here is a comparison between the HTL heavy total quark mass limit cross-sections and the cross-section in the full theory. As you can see, the NL cross-section and the HTL, they are very different. And if you combine the cross-section in the effective theory with the different components in the full theory, for example, the real and the virtual corrections, they have different contributions. So because it is the leading order prediction, here it is a scale uncertainty. The scale uncertainty are relatively large, and also people can study the total quark mass uncertainties. The total quark mass uncertainty are studied by using the pole mass and the rounding MS bar mass. So the total quark mass uncertainty is still very large. It's like 18% at the next leading order level. So if in our work, we plan to include the total quark mass effect in the cross-section level. For example, we can add the high order QCD corrections in the effect theory to the full NLO cross-sections, or we can reweight the cross-section by the leading order distributions in the full theory. And the last way we include the total quark mass effect to reweight the cross-section with the NL distributions. For the last one, we will have a same K factor for the mass corrections. And here it is the summary of the total cross-section in the table. So the best prediction in our paper, it is the last one. So it is the NL reweight scheme. Here it is the pair environment mass distribution, as you can see, with the mass effect for the reweight scheme, we have the same K factor, but the cross section is a little different in the small pair environment mass region. And currently the most precise way to include the top mass effect in the effect theory is the FT approach as shown you as the red band here. The correction is different with what we did here. So in future, we will try to include we will try to use the FT approach to combine with the NQLO calculations. So here is a summary, and I will not read this, but we also, in our work, we also try to predict approximate NQLO distributions, for example, the PT, rapid distribution of the Higgs. And also in future, but the shapes, so what we found is the shapes are stable at NQLL with respect to the NNNLO predictions, and our work paved the way for the precision theoretical studies for Higgs pair production. And in future, we will try to use the FT approach to do the to combine with the NQLO corrections, and we also plan to do the threshold resummation for pair production. Okay, thank you.
Thank you very much, Haitao, for your very nice talk. So any questions? Please raise your hand if so. Okay, I don't see any. So I have a small question, if possible. It's just a detail, but just for my understanding. So on slide 9, so I assume here you, yeah, sorry. So I assume here you have like an assumption for the choice of the scale. So what is the scale that you're using and the variations for the scale uncertainties?
Yeah, we vary the renormalization factorization scale at the same time. So we use the 9-point variation to evaluate the scale uncertainties.
Okay, I see. And then the central choice is like the di-Higgs over 2, di-Higgs mass over 2. Okay.
Yes, yes.
Okay, thank you very much. Any other questions? Okay, I don't see any. So thank you very much, Haitao, again for your nice talk. And so we can continue with Luis with the search for the di-Higgs production in Atlas. So Luis, can you please share your slides?
Yes, I'm about to. You should be able now to see the
Yeah,
slide.
thank you. Yeah.
Okay, so thanks for having me presenting the search for di-Higgs production at the Atlas experiment on behalf of the Atlas collaboration. So I will have just a quick word of introduction, as we already discussed a bit the motivation for di-Higgs. But as you well know, the Higgs potential is governed by two free parameters, mu and lambda. And given the electroweak precise measurement and the single Higgs mass measurement, we can define a rough estimate of the lambda parameter of 0.13. However, this parameter is accessible only through Higgs pair creation, as denoted in the right Feynman diagram that you can see here in green. And usually in experimental physics, we like to quote the coupling strength, that is the ratio of the measured lambda value of the standard model prediction. And as you can see from the top diagrams, there are a wide range of BSM models that predicts very different shapes and thus very different values for this kappa lambda parameter. We have some constraints already from single Higgs production. As you can see that the cross-section depends on this kappa lambda parameter. However, the strongest effect comes from the Higgs pair production, as noted in black in this diagram. The lambda parameter can also be found in the quartic interactions. However, it is way rarer than the Higgs pair production, and therefore it's out of reach even for the high-Lumi LHeC dataset. This will only increase with the square root of S, and therefore is interesting for future colliders. Now, how are Higgs pair produced? As it was already introduced, we have several prediction modes. The main dominant ones is the gluon-gluon fusion, which has a cross-section of 30 femtobars that results from the destructive interference between the triangle diagram represented in pink that involves lambda and the box diagram in blue that only involves coupling two tops, which makes the total cross-section 1,000 times smaller than the single Higgs ones. The also interesting thing is that the triangular diagram is more preeminent in low di-Higgs invariant mass, while the box diagram is at high mass, and that the kappa lambda also changes the distribution of the di-Higgs invariant mass, which has important consequences in the measurement we want to do. Second order is the vector boson fusion, that not only show the kappa lambda coupling parameter, but also vector boson coupling modifiers, which are denoted as kappa 2v in green and kappa v in dark blue. We have also searches for BSM resonances that could show some di-Higgs pair produced with either a spin 0 or a spin 2 predictions for physics benchmarks. Now, experimentally speaking, we don't have a golden channel for looking for Higgs pairs, as we had, for instance, for the Higgs, for the single Higgs. Therefore, we have to split our searches and to combine them eloquently to have an observation. Here in this talk, I will introduce mainly searches that involves Higgs decaying to B quarks, as they have a nice and high branching ratio. And then the second Higgs would decay either to a pair of tau leptons for the log background searches, to another pair of big quarks for the double high branching ratio, or to a pair of photons, which has a very nice mass resolution and that is sensitive to the low part of the MHH signal. I would highlight that the last one is new and was only shown once in Marion QCD 2 weeks ago. I won't touch the di-Higgs to other decays. However, they can contribute, and I will show them into the combination later on. So starting with the BB tau tau found states, we are looking at two different regimes of objects. One that is resolved, looking at low momenta where single objects can be defined, looking at non-resonant and resonant searches, and the boosted regimes where, because of the high momenta of the objects, the decay start to merge and we have to define large objects. So we are defining in both the resolved and the boosted the tau and the B sub-objects, either requesting leptonic and hadronic decay of the taus. And for the case of the boosted search, we have developed a novel boosted decision tree reconstruction and identification of the products, which is very useful in this case. For the B decay part, we are requiring exactly 2 B jets in the resolved case, or in the boosted case, a large R jet that contains these variable radius B type jets. Then we try different fitting techniques depending on the regime. In the resolved case, we do fit a BDT distribution, a boosted decision tree that is trained in different signal regions depending on the trigger and the hadronic the decay of the tau leptons. And we define a non-resonant and a resonant searches focusing at the Gruen-Gruen fusion di-Higgs or spin 0 and spin 2 particles. In the boosted case, we do a single bin fit for different resonant masses expectation, and then we have defined control regions in both of the analysis to control our backgrounds. That results in limits that are placed on the cross-section times branching ratio, or to the cross-section in the resonant case. So for the non-resonant analysis, we can have a limit at 12.7 times the standard model prediction on this cross-section, while different cross-section for the resonances are placed for different hypotheses of spin 0 or spin 2. One can notice that in the boosted case, we are able to extend the range of masses scan from 1 TeV to 3 TeVs. Now let's go to the 4B final state. In this case, on top of the resolved and boosted regime, we have also looked into the VBF case compared to the GGF production modes. In this case, 4 central B-tag jets are required, and for the VBF part, also 2 forward jets with opposite eta signs are required. The main challenge here is pairing the jets. As you can imagine, the combinatorics arising from having 4 B jets, and here it is made making a request on the angular distribution between the pair of jets candidates related to the 4 jet invariant mass, as well as the distance that is computed between the candidates of the 2 Higgs boson with respect to the median median mass that they should have, which is 120 GeV and 110 GeV. How to look for the signal? Here we do fit the di-Higgs invariant mass, controlling the backgrounds through dedicated cuts and control regions. And in the boosted case, we also we do define different categories depending on the number of B-tag jets that are found in the large R jets. In the VBF case, we have similar cuts with respect to the GGF case. And we do place now limits on the same quantities as for the BB tau tau with similar limits on the cross section to about 12.99 times the standard model prediction. And we place limits also on the resonant case for the GGF with masses up to 3 TeV. In the VBF case, we do place also a limit on the cross section to 840 times the standard model. And furthermore, we also place limits on the kappa to V parameters that I introduced before to limits between minus 0.55 and 2.72, minus 0.043 and 256 observed. We do also have limits on a VBF resonant decay to di-Higgs. That is the first time in Atlas we do so. Now let me focus on the BB to diphoton final state, which is new, as I explained, where we request 2 B jets and 2 high quality photons. And here we use the diphoton invariant mass for the fit. However, the di-Higgs invariant mass is still useful. As I told you before, it is sensitive to the kappa lambda parameter for the non-resonant searches. And for the resonant searches, it is also sensitive to the mass of the resonance that we are looking for. Therefore, because of the experimental resolution effects on such objects, we have designed a corrected version of this di-Higgs invariant mass that assume that the 2 B jets and the 2 photons are coming from Higgs boson that are lying at 125 GeV. And you can see the impact, especially on the resonant masses distribution on the left plot, of the nicer resolution for this signals thanks to this correction. Now, how do we look for it? In the non-resonant case, we do train ability in categories that are targeting in 2 mass categories based on this di-Higgs invariant mass. One at low masses that focus on high kappa lambda values and therefore BSM signals. And at high masses, we are focusing on the standard model di-Higgs production. Therefore, we created another 2 categories in those 2 regions, which are based on this BDT that is trained, and we define a loose and a tight category. For the resonant case, we train 2 separate BDTs to separate from diphoton and single Higgs, and we combine the scores in order to create 22 mass categories for these cuts. And then we open a mass window over around the search of the resonance. Now we have the modular background, and for the diphoton, we use a functional form to fit the diphoton invariant mass distribution. And we estimate the bias that we make by choosing this functional form through a quantity that is called spurious signal that evaluate the signal yield from a simple signal plus background fit to the background only distribution. In all the categories defined previously, the exponential form was found to both minimize the number of free parameters and this spurious signal quantity. For single Higgs and di-Higgs signal, we use the same double-sided crystal ball function that is defined in here. And we do apply a yield determination from the theory decided from this cross-section and branching ratio, and the simulation to extract the efficiency and acceptance factor. Now the results presented here are placed on the cross-section of GGF plus VBF for the non-resonant case to 4.1 times the standard model, which is the best result observed to date in any single channel for di-Higgs production. And limits are placed also on the kappa lambda parameters shown here in this plot, which are also the best up to date in this type of searches. On the resonant part, no significant excess is found, and we have placed a limit from 251 GeV up to 1 TeV. Now we have all these nice results and that we can combine, and we did so previously with a preliminary run-2 dataset with 36 inverse femtobarn, and I will show you how they compare to the latest results of Atlas. Looking at the cross-section limits, you can see that the BB NU final set that I haven't presented today and the BB gamma final sites both outperform the former analysis done at 36 inverse femtobarn. And we had also the first look at the VBF, where we have been able in the 4B final state to place a limit on the cross section to 840 times the standard model prediction. For what concerns the kappa lambda parameter, we have also been able to place limits with the BB gamma gamma final set that outperforms the combination only, as denoted in the green band under the plot. In the case of the 4B final set, we have also the first limits on the kappa 2V coupling modifier. Finally, on the resonance searches, the BB gamma gamma and the BB tau tau boosted final states are putting limits that already outperforms the combination that we had before in different mass ranges. For the BB gamma gamma, more focusing at the low masses, and the BB tau tau boosted final state on the high masses. I would like to also highlight the fact that we have the first look at the resonant VBF in the 4B final state, which was not done before in Atlas. So this concludes my talk, and I'm open then to questions from the audience.
Thank you very much, Luis, for your nice and clear talk, and also for the nice results. So any question? Okay, maybe I can start. I have a question for the BB gamma gamma new result. So it's very nice, and you showed that it improves by a factor of 4. So I assume like there is a factor of 2 from the luminosity, but then the other factor of 2 is mainly from the BDT optimization, or it's something else?
Yes, we have several factors that do have an impact. We have first this energy correction on B jets that helps to reconstruct better the BB bar system, which has a big resolution compared to the diphoton system. And as you said, exactly, the BDT also helps really to improve the standard model limit, but also to improve the kappa lambda limits that we place, since now we have a dedicated region where we can look to high kappa lambda values.
Right. Okay. Thank you. And maybe just another question for the prospects. So I know that for the prospect at the LHeC, and a different analysis was used than the one from the 36 inverse femtobarn. So do you think that these results, if extrapolated to LHeC, will even more improve the kappa lambda limits that we have for that?
I can just say that we hope so. Yes. I mean, we have observed that with this very novel techniques that we can place with respect to 36 inverse femtobarn, we gain a lot, and therefore we can hope to get even better constraints. And this said, this work is I mean, is ongoing still, and we have now to renew our studies. And for instance, the context of the snow mass publication could be a nice opportunity for us to show the new results, the new extrapolations. Let's say.
Yeah, thank you very much. So I see a question from Tanya. Please go ahead.
Yeah, can you hear me?
Yes.
Yeah, very good. Yeah, maybe you said it and I missed it. I mean, if you go now, for example, to your slide 17. Yeah, exactly. I'm trying to remember the combination plot and putting it on top of this. I think you are in this BB gamma gamma now with the full run 2. You are, yeah. So I mean, as a function of the heavy scalar mass, right? So I was looking. Can you go back to slide 17? Yeah, I was looking at the right plot. Sorry.
Sorry. Yeah, okay.
Yeah. So I'm trying to superimpose this in my head on the combination plot, which was given, I think, using the first, the 2018 data, and it looks similar. So what is the timeline for a full combination?
I cannot really say anything on the timeline for the combination. There is certainly, I mean, there are also other analyses that are going to be published within Atlas in other finite states. So, so it's safe to say that we are also waiting for them to publish their results in order to have the full combination or the full run-to combination, let's say. However, if I had like the raw numbers for the limits here in these slides, which are hard to compare to this plot. Though you see that already here. So BB gamma gamma was the leading channel for
exactly.
for the low masses, and we are expecting still to be the leading channel for the combination.
Yeah. Okay. So probably similar. Okay, I see. Okay. Thank you.
Okay, thank you. So I don't see any more questions. So thank you very much, Luis, again. So we can move on to Mukesh, who would tell us about top physics at LHeC and FCC-eh.
Yeah, thank you, Nancy. So can you see my slide now?
Yes, yes.
Okay, thank you. First of all, I would like to thank the LHeC and FCC-eh study group on behalf of whom I'm actually giving this talk. So this is just an outline which I wanted to discuss in this talk. I will introduce a little bit of EP collision, FCC-eh and LHeC energies. Then I will talk about charge current top core production at LO and NLO, and how this mass reconstruction of top core can be done at the NLO level. Then I will talk about neutral current top core production, and then beyond the standard model searches. And then I'll summarize and conclude my talk. So to introduce this collider very briefly, if people have already seen Christian-Savinger talk, then I don't need to go into the detail of that, but it's important that I should mention that LHeC have for most of the study, we have the electron beam of 60 GeV and proton beam to be 70 TeV. However, for FCC-eh, we have a 60 GeV electron beam to start with and 50 TeV of proton. And this table is from the recent CDR of LHeC and FCC-eh study group. And this could be seen in this archive, which is going to be published soon in JFSC. So, and most of the things, I think in the next talk also, Uta is going to mention about ERL, etc. So I'm just skipping this for the timing and come towards the topic where we have a top core production in the standard model. So I estimated some of the cross sections and some of the Feynman diagram one can see here that single entire top core can be produced in LHeC with a very high cross section comparing to other channels. And other channels can be, these are some possible channels where top core can be produced with W bosons or in combination with the Z bosons. And also TT bar can be probed in here. And this I did for two energies. So one is for the LHeC, where we have a EP70 eV, and I give the variation from 50 to 300 GB of electron beam. And we can see, comparing to FCC-eh, we can see that there is a difference of about factor of 10 for each cross section. So this is just a brief introduction of how top quark can be produced in LHeC environment, or we can say in E-P environment. And there could be many other channels which can be probed, but I just summarize some of them depending on the cross section here. So let's move towards the second part, where we have to talk about charge current. In charge current, top quark can be produced through this Feynman diagram. You can see here that electron is basically emitting a W boson and giving missing energy. And one has to have the proton as a 5 flavor to get B quark, and therefore one could get n-tight of here. And further, it could be decay into W and B, and W can be decay into either hadronic or leptonic mode. So here is the estimation from this paper, which we worked in 2015, before 2015 basically. And this we calculated at the luminosity of 100 femto-1, all the events here. So in hadronic mode, after having the fiducial efficiency of 66.7% and the background with 61.5%, we can calculate the S over B as 1.2. However, the leptonic channel shows a better result where we have a S by B is equal to 1. So in a nutshell, we can say that LHeC is working as a top quark factory with a very low background. On the other hand, the basic importance of top quark production is that one can measure VTB in the VCKM as well as VTD and VTS. So, and whatever new physics we are getting from there. So here one can take this vertex as a new physics stuff. So we know that in a standard model, VTBF1L is equal to nearly equal to 1. But one can add a term here and try to find what sensitivity we are getting for F1L. Similarly, one can add F1R, and that means the right-handed couplings as well as the coupling which represent to sigma mu term. So, and in this study, basically we did at all the particle levels studies, and we included the different differential distributions as well as cross section, and we got very high accuracy in that paper. But we have updated this study at the Delphis level, and we can see in this figure, this I just show for the hadronic channel, where we can measure the SM-F1L coupling, which is going to determine VTB to 1% level. And similarly, F2L can be measured at 4% and F2R at 9%. However, this is a little bit weak, which is F1R, the right-handed coupling, is 14% at 1 ATO bond. So with this, I can just compare with other collider aspects, and we can see that LHeC at 100 femto-1 itself is working very as the expected sensitivity up to 1% level, and this is very nice comparing to other channels which are going to probe the LHeC. So next I'm going to discuss the measurement of coupling of VTS and VTD, which has been studied in different papers with a different signals. And one can see in here that we have a better sensitivity around 6% for VTD measurement for LHeC. However, for FCC-eh, this has been going to be more accurate, and it could be like 0.037. And this actually extend the HLLHC limits, and the details can be seen in this paper by Hausen, who has given talk in 2018 in DIS. All the studies has been done at the Delphis level. So this is for VTD, and next is for the VTS. So VTS coupling can also be measured with the accuracy of 6% at LHeC. However, for FCC-eh, it is again it's the same comparable to what VTD can do. So this is all about the charge current processes at leading order or at LO. But a recent study just a few days back came with these authors, and they studied top chord production at NLO in leptonic decay mode. And these are the Feynman diagram which one can see at the NLO. So here one can see that there is comparing to LO cross section. This NLO is basically going to be reduced almost by 8.5%, and because of the negative contribution from this channel. And similarly for the fiducial cross section, one can see that LO is reduced by 14%. However, NLO is reduced almost by 15% also. I mean, this is around 14%, this is around 15%. And the fiducial cross section has been taken with these choices of lepton eta and lepton and jets eta, and the PTs are PT of lepton. This is just a standard one greater than 10 GB. However, PT of jet is taken as 30 GB. And then different distribution of leptons and bottom quarks has been studied in this paper. And one can see that this study has been done with the different scales, and also different uncertainty has been taken accordingly. So I'll not go into the detail of that, but it seems that this study shows a very nice representation of NLO QCD corrections. So next, they also calculated very nice thing where they extract the top quark mass by having the transverse momentum spectrum of charged lepton from decay of the top quark. So this is the distribution which one can see of the lepton PT, and accordingly they calculated this all at NLO for full off-shell and non-resonant effects, and the variation of PT can be seen in this table depending on different choices of errors which can come from maybe the alpha S or PDF or mass of the bottom, and also the mass of the top, which in here they have chosen not only the average PT but also the fiducial cross section with the same parameters. And so for 1 GeV changes of MT, this leads to a variation of average lepton PT by 0.12 GeV, which is 0.3. However, the parametric uncertainties are very small, and also they have actually showed that the other QCD effects from various Monte Carlos are negligible. Okay, so with this, this is the study, a very nice study by the group here to extract the top quark mass, where they have the pseudo data with the 172.5 as a top quark mass. And then these bands, basically, if you see the diagonal bands, this diagonal bands actually shows the scale variation, which is varying by a factor of 2 and includes theory uncertainty of 1.3 GeV to extract the top quark mass at NLO. Similarly, this band, which is horizontal one, it shows the statistical uncertainty, which amount to about 1.1 GeV of the for the extracted top quark mass. And these vertical lines basically is the projected uncertainty range of the top quark mass by having various uncertainties, which in the previous slide we had already seen. And upon my request, they have also tried to figure it out that at FCC-eh what is going to be happen. So they just extrapolate this result for 60 GeV and 20 TeV at 800 femto1, and they says that the statistical error can be reduced to 0.2 GeV. So this is very nice result for the studies here. So next we have studied the CP nature of the top Higgs coupling, and we have taken variation of so one can see the Feynman diagram here that this entire top is basically can be produced with Higgs as a Strolong here, and then this coupling is going to be measured very nicely, and this has been shown in this paper by our group. So here ZT is the parameter which we have taken as a variation parameter as an angle which can determine the CP nature of TTH coupling, and kappa is the coupling with the standard model. And various distribution can show, for example, this rapidity distribution with respect to Higgs and top can show how this distribution basically distinguishes the feature with a scalar flipped sign mixture and the pseudoscalar with respect to the standard model. Also, top quark polarization can have a dependence on this CP phase, and that is shown in this figure very nicely. Other plot actually observable, which we have used to calculate the sensitivity or the limits on the coupling or the parameter, the CP parameter. We use the asymmetry between the second B quark and the lepton one, and this plot basically shows that how one can limit at 1 sigma, 2 sigma for the LHeC and FCC. And as for the LHeC for two different electron energy, one is the 61 and 120 GeV. But we have found that this is not better than the fiducial cross-section. So we have chosen fiducial cross-section as an observable, and then we exclude the reasons of the CP phase with respect to the luminosity. And if you read this paper by these people who had worked at LHeC for 3000 femto-1 inverse at 14 TB, LHeC is really doing better at 100 femto-1 itself. And here we have calculated these all things by taking 10% density on the background yields. And with respect to the standard model, we can measure the sensitivity of coupling or the accuracy of coupling up to 70% level. And this studies has been done all throughout the parton level, but it shows that powerful probe of TTH coupling. So next, let's move to the neutral current quickly. And these are the diagrams where one can see that neutral current TT gamma vertex or TTZ vertex can be probed by having this kind of signal. And these are the dominant background one can see. And also one can see that one can measure top quark charge, but I'm not going to the detail of this because of the time constraint. And I'll just show that one paper which basically comes with very nice nice measurement of TTZ and TT gamma coupling, which can be seen here in the EDM and MDM type of coupling, which one can recognize from the Lagrangian itself. So for EDM kappa tilde, you can see this is the precision can be measured within 0.20 to 0.28, which is with respect to 10% and 18% experimental error respectively. And similarly, this could be recognized with the kappa Z tilde, and simply for MDM, we can have kappa and kappa Z tilde. And this is the contour which can show. So this bold line is basically for 10% accuracy or 10% experimental error, and this line is basically for the 18%. So let's move ahead for another part where FCNC top quark coupling can also be measured via the ZTU and ZTC coupling. And in the standard model, we know that this coupling is basically of V minus A structure. And therefore, one can extend this study by having the new physics contributions. So we can have the contribution from, we can write this as a PLPR form as a left-handed and right-handed contributions. And therefore, this is just the correction for the standard model terms, and these are the corrections for the new physics term. And these are some of the cross-section which we have measured and just tabulated with different polarization. So one can have polarization of minus 80%, and then these are the fiducial cross-section by choosing electron as 1 and etc. Very nice distribution. One can see that coupling dependence on the electron angle is very high here, and one can distinguish these two types of coupling very clearly by looking at these diagram. Therefore, we have measured different asymmetries, which was depend on the polarization as well as the forward-backward asymmetry in the lab frame. And these numbers are basically go into an analysis of MCMC analysis with the cross-section, where we extract the sensitivities of the coupling by having this as an assertive formula in the cross section, but this is as the asymmetry error. And then we fit in the chi-square with the luminosity expression, something like this. And therefore, one can see at the one sigma level how this coupling can be constrained in part of 3. So this is basically minus 9.8 times 10 to the minus 3. Similarly, one can count all those couplings here. And the other coupling is basically lambda dependent. So and lambda we have taken just like per TeV, but the couplings are also shown in the part of 10 to the power 3. And this is the table where we have shown the branchings for T2ZU, T2ZC for particular value of the coupling, which lie between the sensitivity range of our studies. So to summarize, I'm going to just summarize this thing, and then after I will stop with my summary and conclusion. So this is very nice plot which has been I taken from Christian Savinga talk in the SNOMAS. This shows the complementarity of colliders to calculate different couplings, which is T2ZU, T2ZC, and one can see from this blue line and this dotted blue line are basically corresponding to LHeC and FCC-eh limits, and this is very well within the collider limits, and somewhere it is really working very good. So if I can see T equal to ZU, so for FCC-eh it is of the order of some times 10 to minus 5. Similarly for LHeC it is between minus 5 to minus 4. So these limits are very well with respect to the colliders and different colliders, and one can just go through the references and see what is happening accordingly. So with this, I'll basically because of the time limits, obviously I didn't included many of other studies which has been already done, but one can see this updated study, updated CDR, which has been published already. The updated version is available now. And therefore, I should conclude my talk here by saying that future EP collider has a rich analysis program, in particular the electroweak interaction of top quark. Single top quark act as a factory, and the measurement of standard model coupling or standard model CKM for TeV, BTV is very, very nice comparing to other colliders up to 1% level of accuracy. Then I talk about the NNNLO production of single top quark in the leptonic channel, and they have calculated the mass, they have done the mass reconstruction very well. And then after I talked about top quark coupling to bosons with WTQ, TT gamma, TTZ, TH, and FCNC. So search of new physics, anomalous top quark couplings, I also included in these channels, and showed that how these couplings are basically measured with a very high accuracy. So we can say that di-Higgs is a competitive and complementary in performing high precision measurements of top quark properties and large sensitivities to be discovered of the new physics, which is lie within the standard model. So I would like to thank everyone and the people here listed who helped me to prepare the slide and also give me an opportunity to present on behalf of LHeC group. Thank you, everyone.
Thank you very much for this nice talk. So I see there is a question from Saleh. Please go ahead.
Okay. Thank you for a very nice talk, Mukesh. May I ask you to turn to the slide number 7?
Sure. Here. Sorry.
Okay. Yes, this one. For the VTD, you have this. And next slide, please.
Okay. Next slide. This one. Yeah.
Okay. Why is the same numbers for TS and TB and TD? I don't understand the reason.
Yeah, the reason is also not clear to me because this is not a full paper. This is just like one talk is given by Hausen. So I'm also not very sure that why these numbers basically are equal.
Therefore, we should check this with Christian because there's some nonsense. I think that for TD it will be something better than for TS.
No, nice suggestion. Yeah, let me talk to not only Christian but also I will email Hobson to see if there is any error
Okay,
or whatever. Yeah,
we can
thank
discuss
you.
this within the collaboration. Okay, thank you very much.
Yeah, yeah. Okay, thanks.
Okay, thank you. There is also a question from Christian.
Yeah, actually, I had a question on page 18. But maybe as a comment here, I think that the reason why for VTS and VTD you get basically the same number is that this is just a cross-section information. Yeah, so this is more or less the same for S and for D. So the difference, you're not sensitive on the difference of the S quark content of the proton in that case. Yeah?
Okay.
Maybe.
Yeah. But I mean, certainly this can be improved. Yeah, but it's basically just the cross-section information, and then you just have the same production mode. Then in both cases, no mass effects, and then they get the same demand.
Okay, this is true for C quarks, but for we have valence quark, D quark in the proton. Okay.
Yeah, but there are many different signal processes, right? And so the one where you take the S out of the proton is only one of 4 or 3 that they're showing. Yeah, and if you, I mean, if you look back to the plots, you see that I don't. Okay, Mukesh, if you want to go back to that slide, then
yeah, this one. Yeah.
And do you have it for VTD then?
Yes.
Yeah, and I think there you see that these other 3. I mean, these are these 3 different types of signals. Yeah.
Signals. Yeah.
And they don't agree, all of them. It is just this one signal 3, which is similar, and I think the others would then differ.
Okay, let me see. Exactly. Yeah. So other signals is something like this one.
Yeah.
So,
okay, I understand. Okay, thank you.
I mean, we can probably
okay.
take this offline, but this is certainly because it's only true, I think, for the signal 3.
Yeah, you consider on the electron version, not with positrons. Okay.
Yeah.
If
Exactly.
they have all the electron beams, then okay.
Yeah. Okay, then I have a question on page 18 then. Yeah.
18, yeah.
I mean, your limits, yeah, if you compare them, I mean, if I would see this correctly, the VTZ, and I'm sorry, the T to ZU limit, that would be, let's say, 9% for the left-handed and 0.009%. So this means 9 times 10 to the minus 5. Yeah. How does this compare to the next slide, to the summary plot?
Yeah.
If you go to slide 19, then would it really show up at 10 to the minus 9, right? In the last entry below, yeah?
No, for the branching, obviously this is clearly at -3, and this is also in the order of -3 actually.
Okay.
Yeah, this is not -5. Yeah. So
I thought it's in percent, so then it's -5. Okay, because
exactly. Yeah.
Maybe we should then have a look how this differs from what is in the plot for the Orhan et al. Calculation. Yeah, but probably because you lose only the left-handed ones and stuff like this. Yeah.
Yeah. Yeah.
And I have also another question. I mean, this very interesting extraction of the top mass. Do the authors actually comment on this? You know, that the problem is always at this precision at the LHeC, how the extracted top mass relates to an MS bar mass or to a pole mass. Anything to gain in
the paper they haven't mentioned about these things. Yeah.
So do they think it helps in this interpretation thing?
Well, it was very quick actually. They just have the paper, so I didn't get a chance to discuss.
It just came out at end of March.
It just came out. Yes, right. Yes. So
that
I
might
just
be
saw and commented.
Option.
Yeah. Exactly. Yeah.
Thanks so much. Yeah, great. Thank you that you found it.
Thanks. Yeah, no problem.
Nice talk.
Thanks.
Okay. So thank you very much, Mukesh. We need to move on. So we can go to Uta now, who will tell us about Higgs physics at LHeC and FCC-eh. Uta, can you please share your slides?
Okay. Just a sec. So now you could see, hopefully, my full screen. Can you hear me?
Yes, we can hear you. I can't. Okay, yeah, now I see the full screen. Yes, thank you.
Okay, very good. Thank you very much, Nancy, and all the organization team for all the hard work to organize this online conference. And it's a pleasure for me to point out some highlights on standard model Higgs physics that we may do at a Large Hadron Electron Collider, or then even an FCC-eh. So we like to add electrons to our high Lumi Large Hadron Collider. Why? Because this proton-proton collider, it's such a unique multi-billion investment that if we adding there a 60 GeV energy recovery LINAC, which has a very reduced power consumption. Yeah, so everybody is quite excited about all the energy savings that we can do during COVID times, but here we can really save energy. Let's say standard LINAC would need 1 gigawatt, and we can produce the same 60 GeV with less than 100 megawatt, and this without any radioactive waste and with high electron beam polarization. You see here the structure, and here are our high Lumi LHeC protons, and then we hope to achieve in this way center of mass energies of amazing 1.3 tera electron volt, which is factor 4 higher than Hera. So this is a unique twin collider idea that also holds, of course, for any future proton-proton collider. So this is quite amazing. So what can we do there with standard model Higgs production? And here you see on the graph on the upper left plot, we have our electrons that our energy recovery structure is delivering us with high polarization. And then we have our, let's say, high luminosity Lumi LHeC protons. And then we can have either the WW vector boson fusion, which we immediately know because we have the missing energy in the final state and a forward jet, or if you go to the right-hand side, we have the ZZ Higgs. So this is really, and then we have, of course, a scattered electron. So we have this very well defined direction of what is really our scattered squark in comparison what we are doing in vector boson fusion at the Large Hadron Collider. You see here on the lower table some leading order QCD cross-section, and all these cross-sections that you see in particular charge current, it's around 200 femtobarn at the LHeC and 1 picobarn at the FCC-eh. So this cross-section, it's very similar to the Z cross-section in E plus E minus, because here, because the production mode, it's different in plus E minus, but let's say the order of magnitude of the cross-section is very similar, and the 1 picobarn is even higher than the cross-section at click. Yeah, so we are speaking about interestingly high cross-sections for this process. For the theory, of course, this is leading order, but on the other hand, this is vector boson fusion, and everybody who is doing proton-proton physics knows immediately in vector boson fusion, we have the theory better under control, and this also holds here for electron-proton vector boson fusion. And as you may have heard, this is a very nice talk by Claire Gwendolyn, and I gave here the reference numbers so that you can easily find the abstract, is that we have the full self-consistent framework. We have the n-cube leading order PDFs, we have the charm mass, we have the bottom mass, we have alpha S to per mil level, everything within one experiment, with this high energy frontier electron proton collider. So this is really a full new world of unfolding PDFs and Higgs. So this is just a word on this slide on the electron proton kinematics, because we are using MATGRAPH and then showering and then Delphis, but this is just to see here for the FCC-eh, that what we are doing, even with the scale of the PT of the leading jet, which is not really a favored scale to describe there, as we get sensible distributions in our simulation. And here you see on the upper right plot the amazing kinematic reach with this blue band for the LHeC and the brownish one on the Bjorken X, which is on the x-axis, and the mass scales that we can reach. And this is, of course, an amazing, amazing potential that we have. Usually we are getting the question, oh, why it's all so asymmetric? just a 60 GeV electron, it's somehow like scattering of a brick wall. If it's somehow this is 50 TeV protons, for instance, for FCC. Is it doing anything, and is it contained in the detector? And so that's why I put here the plots for the pseudo rapidity in the detector on the x-axis. And then you see our Higgs is really still nearly centrally produced, and also the decay. So the decay is really nicely following the Higgs. And then we have these gaps. You see the graph, and then we have something like rapidity gaps due to the scattered lepton or the missing energy and the forward struck work. And this is what we're actually using then also, for instance, if I then show in a couple of minutes when we even here like to detect Higgs is decaying to WW. So the rates and geometric acceptance play, of course, an important role. And we made here our CDR update where you see here the dark black line. This is that we assume that we have a forward jet acceptance of 5. This is what we have as Atlas and CMS. And then we see that if we then have just say, okay, we even like to have the Higgs decay products within, let's say, a reasonable pseudo rapidity range of 3.5, so it's a couple of degrees, then the acceptance is 70%. For FCC-eh, of course, due to this larger asymmetry, it drops down to 57%, but it's nothing that we really have to worry about too much. It's still all feasible. And if you may think even about very rare decay, because here you see the table for typical rates, so that we have thousands of Higgs to BB bar decays for LHeC, and also for FCC-eh, we see even more. We expect even 1 million of those. And of course, this scales also with a running time, because everything electron-proton collisions, of course, it's bound to the timeline of the proton-proton collider. So we have rates, we have acceptances, and we may even do then Higgs to mu at FCC-eh, if you have a muon detector which goes up to 4, which is in the range of 6% for the single strengths. But more on this later. So of course we have the Higgs to BB bar, and this over the past years we did quite a couple of studies, starting from parton level, going to the various PGS. This is perhaps, you may remember, pretty good simulator, then to Delphis, producing single samples, all kind of multi-jet and top and Z and other jet production backgrounds. And here you see in those plots, and the left-hand side is for the FCC configuration and the right-hand side for the LHeC, so the different center of mass energies. We assume even no polarization of the electron beam and just one standard year running, because of the high luminosity. And you see here these dark points. This is the Higgs peak out of the background. Just doing simple straight cuts, we would expect to see a Higgs peak in BB bar. But then, of course, we wanted to go more for position. And then, so we changed a little bit the attitude. We just made looser cuts, and so that we can pass it on to the boosted decision tree. So that we make just loose cuts. We have all the backgrounds, all the multi-jets here in purple. We see here the Z peak. We see the W peak from the top production. Then we do a heavy flavor tagging. And this is, again, just the di-jet spectrum. And even in the di-jet spectrum, there's no B tagging, nothing. Then you would see already an excess. You would see an excess. The Higgs peak would show up. And this is, of course, that we used. And then we put this to a BDT, and all this again that we get then better single strength position. And this is summarized here in this plot, and which is also described a bit more in our update of the CDR. And doing so, and then you see here the remaining Higgs to BB bar peak, which is quite similar to our Atlas peak, by the way, somehow from the shapes, also from the background shapes. But of course, we have cleaner signal to background conditions, and we even can tackle charm. And this is, of course, very nice. And I also cross-checked forward and back what we're getting here. also with efficiency assumptions. And this is a text that you may look through this in comparison to an E plus E minus ILC study. So we think that we are getting Higgs to BB bar, a nice single strength of less than 1% for Higgs to BB bar and around 7% for Higgs to charm. But what is really striking is, can we do something with Higgs to WW? And this is the graph that I put here in the green box. Yeah, why? Because we have a WW fusion to a Higgs, and Higgs is decaying to WW. And now, if we now assume standard model, so there's nothing in the production, nothing hidden in the decay, then we have, and this is what I put here, the beautiful relation that only with this measurement, we can directly go to the coupling, yeah, so that we have direct access to the coupling, only from this one. And this, I think, it's pretty cool. And this study, this is, I did in the for the CDR, for the FCC CDR, so that's why it's for the FCC-eh energy. So it's for the very asymmetric configuration, and also assuming all the proper branching fractions and the decays, and so that we get something like this 100 femtobarn and pass everything through our FCC-eh deltas detector. And of course, the backgrounds are all these guys which are here around. So this is, of course, a lot of things, and how one is doing resolved jets. So yeah, because of course we have much more methods developed with Atlas and CMS that we also can have merged jets. Yeah, but this is not considered. It's only resolved for resolved jets. And also studying which anti-KT algorithm. So I was ending up with 0.7. So this is just somehow like the first glimpse of the power of the method. And here on this plot, on the analysis strategies, and this is on Delphis detector results, and this is really done employing these gaps that are open up, and that the Higgs is always tending, that the decay is decaying, yeah, giving back these most central Higgs in comparison to the other stuff, and there are no mass constraints in. Yeah, it's not like usually the Atlas and CMS that we assume this mass, nothing in. And if you do so, and then you can also check the purity, the truth matched, yeah, of the method, which is on the left-hand plot, and on the right-hand plot is then what my reconstruction is doing. And then of course there are still some not so super duper features, but everything is there. We see the real W, we see the off-shell W, and we see the Higgs peak. And only with this method, yeah, we get a Higgs to WW single strength in the range of, let's say, 2%. But due to this 1 to the 4th, yeah, this relation, we get a Higgs coupling, Higgs to WW, which is, let's say, 0.6%, 0.5%. So it's extremely powerful. And this is really totally complementary to any E plus E minus collider. This is then our summary of all the Higgs single strengths that we may get in electron-proton collision. And you see here the light blue for the different proton energies, so that we have always 60 GeV energy recovery, which we then merge concurrently, twin collider idea, with either the 7 TeV of the LHeC, or a high energy LHeC 14 TeV, or FCC, which is 50 TeV. And then you see that all these nice sub% here, because it's all usually very nice for the neutral current and the charge current. Then we can have also standalone copper coupling fits. Yeah, this is here like similarly like the click model dependent method, where I cross-reference this here. And then you see here again the power of the WW. And you see that the BB, although it's our most precise channel, it's a usual effect that BB sacrifices its position in the single strength to all the other channels in the coupling fits. Yeah. But overall, we see from this plot that we may have, due to this combination of the charge current and neutral current, yeah, because it's event by event, we know is it WW or ZZ, we can measure those and combine those. Then, of course, what's really interesting if you combine now, because it's running in parallel, And as Claire Gwendon was showing so nicely, even with the first 3 years, if it would run, we would immediately give impact to our ATLAS and CMS results. And this is the slower plot, because this is just an arbitrary unit. Let's say, if you really would change alpha S in a more generous way, yeah, who knows what alpha S really is. But in EP, we could measure alpha S very precisely, and then you would get here this little band. So we would have our proton-proton Higgs cross-section would be better known than 0.5%. So this is really, really, really cool. And we would add charm, let's say, from the couplings, and we would add the Higgs to WW, we would add the BB bar. So this whole beautiful picture of LHC and an LHEC would be just amazing. And even if you would go to further future, and this is, you may see, ah, wow, what is this plot? Yeah, but this is really everything. It's getting more and more complicated. Yeah, so then to make a full unfolding of all the couplings and even then the widths, etc. And if you add here just that usually it's celebrated that we need E plus, E minus, and HH, yes, but then you have these kind of correlations because of the ZZHH, because this is the can't hardly be resolved by this combination. But then, and these crosses I was doing, that these crosses you can only remove if you add an electron-proton collider, like LHeC and FCC-eh. Then you resolve this ambiguity. This is then resolved. So that's why all these 3 colliders are really, really important. And those only give us then the full picture. And I have all the tables over in the backup, and also Sally Dawson was mentioned this in her plenary talk already. So the wrap up, so the LHeC and FCC-eh really could measure the dominant Higgs couplings, the first 7, and including TTH, as shown by Mukesh, to really high precision. And I was not mentioning all the stuff that we have no pileup, yeah, but we have the clean final states, similar cross-section like E plus E minus colliders. And again, these Higgs measurements in electron-proton are really self-consistent. Yeah, experimentally and theoretically. It's all one, yeah, it's one detector, one full framework also in the theory. Yeah, based on the DNS cross-section measurements, so with this very small systematic uncertainties. And then I just flashed that there's also this striking synergy. If you would have an energy frontier electron-proton collider, which center of mass energies beyond 1 tera-electron volt, and the E plus E minus colliders, which are 250 or 350 GeV, and then our LHC proton Higgs results. Yeah, it's all those 3 may then bring the big picture together and remove the HZZ or HVV and these further correlations. Yeah, so that this energy frontier electron proton would really empower the physics potential also of proton-proton. So non-resonance searches, all the electroweak fits, which we also discussed in a minute with Daniel and Higgs. Yeah, and we have this very high precision QCD. So combining these proton-proton with electron-proton gives a very powerful Higgs facility. This is twin collider. And we could reach this for the high-Lumi LHC already in the 30s. And then, of course, if we plan ahead for FCC-eh, we just should add an electron ring. Yeah, thank you very much for listening.
Thank you very much, Uta, for this very nice overview. So any questions? Okay, maybe I'm just, sorry, I couldn't download your slides. I had a previous version, but you showed like 3 graphs for these couplings, for precision of the couplings. I was a bit lost of the difference between them. Sorry, I cannot say.
Yeah, this one, yeah, okay, because out of time I was. So the light blue, it's somehow the expectations for the high-Lumi LHC, what we expect from ATLAS and CMS in the kappa framework.
Yeah, right. So I understand the graphs, but I didn't understand the difference between them because they are a bit different. Is this just like a different version or?
Oh, what is different version? No. So you have the light blue. It's somehow if you would have just our ATLAS and CMS best scenario after high-Lumi LHC is finished. It's a light.
Yeah, no, I understand, but just between the slide, I think the next one, sorry, I don't have your slides downloaded. I'm trying to,
Which
it's
one?
very slow.
Oh, Uta, if you go before, then there are a number of...
This is the standalone coupling fit if you would have not only LHeC, but also FCC-eh with different energies, with different center of mass.
Okay, a different energy. Okay.
This is without any proton-proton. This is any plus or minus nothing. This is just only the various high energy frontier electron proton collider options. Yeah, thank you for asking. Sorry if I was unclear.
No, thank you. Okay.
Electron proton colliders, yeah, even the LHeC of course would give a start. But of course, if you go to higher and higher energies, of course, we have then this dramatic increase in the cross section. Even here, it's 1 picobar. Yeah, it's a 5-fold cross section, and this, of course, is showing off in the precision of what we may expect.
Yeah, thank you very much. And what, sorry, just since we had the di-Higgs talk before, so what would be, you didn't maybe mention for the di-Higgs? For the
di-Higgs, so for the LHeC, the di-Higgs cross sections, of course, very, very small, but I think I put one, we did the study a while ago. Here, this is for the double di-Higgs production, which we studied for the FCC-eh, where you see again that you have the beautiful graphs, that you have the WW goes really into the di-Higgs. And then we also have so this is really the self-coupling in the first graph, and then we have the di-Higgs production, and then we even have the WW Higgs production. And this is the studies that we did together with Mukesh, so in case Mukesh can answer. But we hope that we may get something like 20%. Although then this was again a cut-based study, yeah, and we think that with all these extremely better neural networks, we can also go with lower luminosities, that we may reach something like 20%. And again, the graphs are complementarity to what we may expect from proton-proton. This is pretty nice.
Thank you very much.
Welcome.
Okay, I don't see any more questions. So thank you very much, Uta, again. And we can move on for the last talk from Daniel, who will tell us about the precision electroweak measurements at LHeC and FCC-eh. So Daniel, if you can please share your slides.
Hi, do you see my slides now?
Hello, yes, I'm not sure if everyone sees them in the full screen because me not yet.
Screen. I can make it full screen. Wait a second. No, full screen. No, it's not full screen. It's not. No, better.
Sorry, for me it's slow. I don't know if everyone sees it.
Yeah, much better.
Okay, thank you.
So you have it full screen. You see my cursor and you hear me. Perfect.
Thank you.
Then we can start. So I'm presenting prospects for electroweak physics at the LHeC and FCC-eh, and work done with Max Klein, Hubert Spiesberger. So I'm considering in this study basically the basic neutral current and charge current as cross sections. Very well known. So the electron scatters off the proton, and the process is mediated by a photon, by a Z boson or by a W boson. And basically this process is mainly used for studying the QCD dynamics or basically other finite states. But here in this study now we are particularly interested in studying the sensitivity in this weak or electroweak exchange of the Z and of the W to fundamental parameters of electroweak theory. In particular for the FCC-eh and for the LHeC. So Mukesh and Uta and many others have talked a lot about it. I briefly just repeat. So basically the FCC-eh attaches the electron beam to the FCC hadron. For this study here, we expect that the electron beam has 60 GeV The proton beam has 50 TeV. This results in center of mass energy of 3.5 TeV. And we expect that we have an integrated luminosity collected of 1 inverse attobahn. The LHeC is much closer in time potentially. So basically a similar accelerator structure can be attached also to the LHC, or to the high Lumi LHC then at this time. And then we have basically collisions of 60 or 50 GeV electrons with 7 TeV protons. So this results in a center of mass energy of 1.3 TeV. And also here we expect that we have an integrated luminosity of 1 inverse attobahn. Detector here may be shared maybe with proposals from LHeC. So this is under investigation. And also we must consider that while it may be very expensive for the first instance of this accelerator, the accelerator structures can then be relocated to the FCC in the future and can be reused also at later times. So the kinematic plane was also already discussed a lot in other talks. So I would remind you that here for electroweak physics, we are particularly interested in high Q square, so at the kinematic level, and also at high X. And this is often denoted here sine square theta in this plot, if you have seen it already earlier. So coming to electroweak physics, where do we stand essentially? So basically most of the precision electroweak measurements have been done at lab at the Z pole, where basically they measured exactly this huge kinematic peak or this huge resonance of the Z with very high precision with 4 experiments in lab and also at LHeC. And lab 2 then also further measured above the boson resonance, boson threshold up to several hundred of GeV. But you see that this cross-section is significant. So basically one is largely statistically limited with the depth 2 measurements. And this is also what we see nowadays. So if you look into the sine square theta summary from the PDG, so this sine square theta and the MS bar scheme, we have these few measurements at the Z pole from depth, from LHeC, also from LHC and Tevatron. So they're just displaced here for visibility, but they are exactly at the Z pole. And then far away, there's simply nothing. There are no precision data, no precision measurements. It's only basically a theoretical prediction how electroweak theory or basically electroweak interaction at all are realized in this regime. And only at low energies, then we have, again, measurements of the weak mixing angle. But we don't know actually how electroweak theory behaves in between this region here. So how does this look like in DAS? DAS is completely mediated in the space-like regimes. In the T channel, we don't have any resonance, but we have neutral current and charge current cross-section at that time, and we have a scale dependence. So this is the cross-section, the polarized electron-positron cross-section for neutral current and charge current interactions for the 4 experiments, so for LHeC, EIC, FCC-eh, and HERA. Also here we have H1 data points included in this figure. And we see the basic about the electroweak scale, which is about 100 GeV or 10 to the 4 GeV squared. This EIC has the strong drop. HERA had a glimpse of data, but basically here where the electroweak scale or the charge current, neutral current cross-section become of similar size, we are at the kinematic edge and the cross-section strongly drops. And I see here these large statistical uncertainties already at HERA and LHeC. We have a factor of 10 or even larger cross-sections. And we have this huge additional kinematic region Q square where we have strong contributions from gamma Z and Z exchange terms to the cross-section. Also, we have about 1,000 times higher luminosity than at HERA, or basically 2,000 times more luminosity than H1 alone. So basically you also go much further down here in cross-section, and FCC-eh would even go further, which is not even more on the figure. Note that at low Q square, basically, we are limited by photon exchange and neutral current, but charge current cross-sections are always mediated only by pure W boson exchange. In theory, this looks like that. We have the inclusive neutral current DAS cross-section formula as a function of X and Q square. This is widely known. This is a decomposition to the structure function approach. I must say, this goes back to Thord Riemann, who said he passed away last week. So we should remind him at this point, and also he made famous contributions to electroweak standard model altogether. So these generalized structure functions here, they are decomposed into the photon exchange, the photon exchange, the gamma Z interference term, and the pure Z exchange term. They always come with a normalization factor, which basically normalizes the Z exchange with the Fermi constant to the photon exchange with the alpha, even electromagnetic with fine structure constant. In the on-shell scheme, this is expressed in terms of just the ratio of the 2 weak boson masses, the W mass and the Z boson mass. Here, this is this normalization constant. And then we have also the propagator term for the Z boson. In addition, then we have the couplings. So we have the vector coupling, the axial vector coupling of the electron. And of course, for the C exchange, we have then squared in the expression. Similarly, at the quark vertex, we have then also photon exchange, gamma Z exchange, and we have the pure Z exchange. We have again the vector coupling of the quarks and the axial vector coupling of the quarks contributing to the cross section. These couplings are predictions by the model. They can also be considered to be standalone, but they are predictions of the model, and they also include basically higher order electroweak corrections in terms of form factors, rho and kappa. So how we study now electroweak physics at the LHeC or FCC-eh. So we simulate inclusive neutral current and charge current as cross sections data points. So here you see the kinematic plane where our data points are located. We have about 1,200 cross-section data points with a full set of systematic uncertainties. These include all these experimental uncertainties, and also background uncertainties, and also radiative corrections, normalization corrections, efficiency corrections, luminosity uncertainties, and all that. The same data set is commonly used for PDF prospects at these two experiments. So maybe you have already seen some of these results earlier. So then we perform also a PDF fit. This is because at the time of the LHeC, all the PDFs will be determined from exactly that data. So any reasonable estimate should include a PDF fit plus something else. So this is what we do now. We have a next to next leading order QCD PDF fit. And in addition, we have then a fit of the electroweak parameters of interest in our study. The electroweak calculations include all the one loop corrections in the on-shell schemes. Our free parameters are defined structure constants, MZ and MW. And then we have all these correction factors, for instance, delta R, where the dominant contributions come from rho T with the M top dependence, and also the logarithmic M mixed mass dependence. So essentially, sine square theta, GF are calculated quantities, and also more generally, also the vector and the axial vector couplings are predictions, but they can also be considered to some extent as free parameters, and we can test their consistency with the expectation. So let's have a look into our expectations. So the first expectation that I want to discuss is the W boson mass. So here we determine the W boson mass together with the proton PDFs. And for instance, for the LHeC, the 60 GeV energy, and we expect that an uncertainty of only 6 MeV. For the FCC-eh, we expect an uncertainty of only 4.5 MeV. These numbers already include the PDF uncertainties. For instance, for the FCC-eh, these may be as small as 3.6 MeV, but they are already included in this small number. So if you compare with measurements from DEP2, for instance, so this is a combination of all the other of the DEP experiments, Tevatron and Atlas, this is of course a very, very competitive and superior precision. Contrary, unfortunately, you must say that this is of course not, it's just an indirect determination. This is not an on-shell value. So this is more like a consistency test of the standard model. Its relation to the real W mass, it's not, it's difficult. But this is a very, very stringent and high precision consistency test of the standard model. More commonly, often people consider this effective weak mixing angle of the leptons at the Z boson, at the Z pole. This is because from asymmetry measurements, basically these rho factors cancel out, and one can measure in plus and minus at the pole exactly this quantity kappa times sine square theta. This is also done at Tevatron and LHeC, so we can similarly do such an extraction in DAS by accounting for small Q-square dependent and flavor dependent corrections in the theory. This is similarly done also for the other experiments, so this is not something very special. And by that, we can determine the effective weak mixing angle in a very, very similar way as is done basically on the Z pole. And we expect that we have an uncertainty on this measurement of 0.00015. FCC-eh again will be superior with 0.00111, and here the PDF uncertainties or PDF related components of the uncertainties will be even smaller. So if you compare basically the expectations from LHeC 50 GeV or 60 GeV electron beam or the FCC-eh, this will be again superior to the measurements at LHeC Tevatron LHeC plus SLD. This is a very, very highly competitive measurement, a very precision measurement. But I mean, why we want to measure this effective weak mixing angle is because it's effective. It means that basically it includes loop corrections. The loop corrections are sensitive to beyond standard model physics, to everything that is heavy, because either there are heavy additional gauge fields, or there may be additional heavy quarks, but they must also couple to the Higgs and so on. And this should all show up basically in these form factors. But this must be particularly sensitive then also in the scale dependence. And because we are measuring over such a large Q-square range, which is very unique to DIS and very different to what we know from the Z-pole measurements, we can test the scale dependence or the Q-square dependence of the weak mixing angle. And this is shown here on the left plot. It's a relative uncertainty on here the on-shell weak mixing angle, and we see from these three studied cases for the FCC-eh or from LHeC, we reach per mil uncertainties in a region of say 20 GeV up to a few hundred, 600-700 GeV for LHeC, and even to the TeV regime for FCC-eh. And this is particularly the region where we don't have any precision data nowadays. So basically this connects the Z-pole measurements to the low energy measurements, and we basically make this bridge where we currently don't have precision data. And also we see for the first time basically how electroweak theory behaves at high scales, and we measure this entire large range here up to the TeV regime with a set per mil precisions. So here this is in the MS bar scheme, so the calculation from the on-shell scheme to the MS bar scheme must be done. This is a small theoretical factor that is not accounted in our study here. Similarly, then we have basically higher order corrections. So I said the top quark mass plays a particular role in these corrections. In the dominant rho T term, it always comes with a ratio of m top squared over mw squared, and commonly basically the electroweak community studies then these global fits. So they are different flavors. So LHeC and SLD have determined the W mass and the top mass simultaneously and have this large band here. In the global fit, if we add more data, then basically you add 1 degree of freedom, and you see basically you just cut out this degree of freedom here. This is from a G-fitter result. And we can compare our indirect determination of MW and MTOP with these results, and we see that we are very, very competitive. And it's not a surprise, but it's just a case of the physics behind it, that basically the correlation between MW and MTOP here are exactly the same. This is because we test exactly the same higher order corrections, or the same theory that is behind DIS and behind E plus, E minus, or PP physics. One can make the game and say, okay, if the W mass would be known with highest precision, we would get a top mass uncertainty of 1.1 GeV, and for the LHeC and for FCC, we would have a top mass uncertainty of 810 MeV, which would be, of course, very, very precise. And so in exact pole mass definition, this could be compared to equally very measured direct top mass measurements at the LHeC in the future. Other high order corrections are included in the rho term. In the kappa term, we already have discussed to some extent, but we can, of course, perform a simultaneous simulation of the rho form factor together with the kappa form factor. These are the factors basically that multiply with the axial vector and the vector couplings. You see them here. And they have been also measured in a large extent at LHeC, also flavor dependent here, because they are just a single modification of these anomalous couplings. And we see that basically we have also, again, here for this 2-parameter fit, competitive expectation and the combination of the LHeC experiments, but we have a different correlation. This is because we have a simultaneous explanation. We cannot disentangle these 2 parameters, and that basically measures the kappa F separately because of these asymmetry measurements. Again, here of highest importance are potential deviations due to non-standard model physics, which can show up in the Q-square dependence. And here we can also measure the Q-square dependence at very, very, very high precision. You see, if you have per mil uncertainties, again, in the region from 20, 30 GeV up to 700, or the FCC-eh to up to TeV regime for the rho factor and for the kappa form factor. We compare here with H1 data, and they see it is possible to do these measurements, but at error, we have these very, very, very large uncertainties. One other highly interesting parameter are the light quark weak neutral current couplings. It's a bulky name. It's basically the couplings of the up quark and the down quark to the Z boson. They are theoretically predicted, but they are poorly measured. You see the measurements here from LEP. We cut out this banana. It's this huge banana. We have the D0. It's also a large, huge area here, also the D0 area. And then the H1 measurement, I must say that also Zeus has a very similar measurement in H1. And with LHeC or FCC-eh, we can constrain or determine these parameters with very, 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 very high precision. This is because we have very high Q-square and we have very, very high luminosity, which allows us that we go to high X, where the PDFs are precisely known, and therefore we have an exact vertex of a Z to an up quark or a Z to a down quark. And for the first time, I think we can measure these very, very important quantities with very high precision. Other parameters which are commonly studied in these electroweak studies are generic parameterizations of beyond standard model physics. These are the so-called STU parameters. Here we have performed a study of the two of these at a time, so ST, TU, and SU. These parameters are dependent on the scheme of the calculation, so therefore it's not straightforward to compare our expectations with the present best measurements, but you see that basically we can constrain all the three variations, all the three parameters together. This is because we also include charge current cross sections, and therefore they become complementary to the Z-pole measurements. And we reach uncertainties of, say, 10% or so on these three different parameters. One very, very unique and last prospect is charge current measurements. So we always think about just neutral current quantities. We talk about electroweak precision measurements, but of course, electroweak contains also charge current. And here in DIS, we measure the charge current jet in the detector. We know about the initial state electron, and therefore we can reconstruct exactly the kinematics of the event, which gives us a very precise measurement of charge current. And charge current have a very similar structure than neutral current. So we have, again, form factors. In charge current, we have only two of them. We have an electron quark and electron antiquark form factors. And this allows us now basically to determine also these two form factors, or essentially we have anomalous form factors. We add this anomalous parameters, this prime parameter. And we expect that for standard model, these are 1. And we see that basically these can be also determined with percent precision or per mil precision even. And here's one result from H1. This is a very, very huge area here, which is a bit offset, a bit far away from the expectation, but maybe not too much. And again, here we can also study for, with a very unique manner, the scale dependence of charge current interactions over a very, very, very large kinematic region. And here we are not limited at low Q-square by photo exchange, but we can just go down as much our trigger will allow us to measure. So with very high precision. I will skip this slide because I want to spend one more sentence on the complementarity with the high Lumi LHC, which is very important to my impression. So we always talk about it and make a comparison with LHC, and we want to know basically what will LHC deliver in the future on these important parameters. And in the yellow report, there are these two prospects on the W boson mass determination, also on sin square theta effective. And we see that basically nowadays, these measurements are completely or largely already limited by PDF uncertainties. And even with a very optimistic PDF expectation, they may be reduced from 8 MeV to 4 MeV, but only with the PDFs that will come from the LHeC, this dominant uncertainty will be reduced to a factor where really the uncertainties from the Lumi LHC will be the dominant one. So basically the LHeC PDFs will become very, very important to measure at all W boson mass at the high Lumi LHC. And similarly for the sin square theta effective, here it is even seen that basically if the LHeC PDFs are included in the determination of the effective mixing angle, the uncertainties are reduced by an additional factor of 5. So the PDFs are very, very important to support precision measurements at the Haitao LHC in PP collisions. Summary. There are future DIS experiments foreseen at CERN, or not, I don't know. The LHeC with 60 GeV times 7 TeV proton and FCC-eh. About the electroweak physics, I've presented a few benchmark studies. Basically, we see that fundamental electroweak parameters can be determined from inclusive DIS cross-section measurements, and they are very competitive with present data and maybe also competitive with future data. I must say they're often complementary, but many different aspects of the electroweak standard model can be tested and also can be measured uniquely in DAS, which otherwise are not tested. Therefore, maybe people don't think about even such possibilities for such measurements. And also, of course, we can have a global fit. We can determine the PDFs, we can alpha S, top masses, and all the electroweak parameters together in a single process from a single experiment in a single framework, which I think is a very unique and brilliant possibility for a consistency test. Also, we see that basically the LHeC PDF is really important for PP in the future. References here, the update on the CDRs on the archive is accepted for publication. We have a paper on the electroweak studies for LHeC in EPJC, and we have updated studies for FCC-eh shown today, but also partially in the FCC Physics Week in November last year, sorry. So thank you for listening.
Thank you very much, Daniel, for your very nice talk and the nice results. So any questions for Daniel? Oh, okay, I see Max, please go ahead.
Yeah, Daniel, everybody, since it's getting dark in Berlin, what is the background of your summary slide? Is this Hubble telescope thing? Is this LHC?
I think this is a flash picture from FCC Physics Week from CERN.
I see.
I think this should be the future to some extent at CERN. And this is light and dark. You see, you have dark matter and you have light matter on this picture.
Okay. Thank you, Daniel. Thank you very much.
Okay, thank you, Max. I see Arif, please go ahead.
First of all, I would like to thank Daniel, Max, and Hubert for preparation of this very, very nice and comprehensive talk. But one small question. In the beginning, on some slide, I have seen the value of radiative correction about 0.3%. It is maybe before. Here, this.
Mm-hmm.
So I would like to ask, it is this value belongs to some charge current, neutral current, deep elastic scatter, or to what?
Yeah, this goes back. So I comment, Max. I try my best. Okay, and this goes back to basically studies from HERA 1, where basically these electroweak corrections have been studied in great detail, and you have to correct the data at least for these structure function measurements. How we present them here, consider them here for real photon radiation. At the time when these were done at HERA, these corrections were expected to be known by an uncertainty with 0.5%. Maybe this will certainly improve in the future, but maybe even more.
I now understand. This is uncertainty for radiative corrections, no?
Yeah. It is.
Okay.
It's an uncorrelated uncertainty on the radiative corrections, which ties bin to bin and which accounts for the unknown correction of
now I understand.
Photon, initial state and final state photon.
Okay. Thank you very much.
And it relates basically with the reconstruction method that is used for the reconstruction of the DAS kinematics.
Mm-hmm. Okay.
Arif, is this you?
Yes, I am.
So thank you very much. So mean, this is after the E minus BZ cuts the residual uncertainty, which we think. Daniel said. I only wanted to say hello to Arif. Thank you.
Okay. Yeah, I am also tell you hello. Thank you. See you in the future. Okay. Bye.
Thank you. So Daniel, maybe I have a small question on your slide 11 for the W mass uncertainty that you quote like 8 or 6 MeV. Yeah, sorry. It's just so what goes there in exactly? So this is like the PDF and the experimental part.
So this is basically in the framework that we consider as free in this fit, which are the PDFs and the W boson mass. This accounts for all the experimental uncertainties of the neutral current, charge current data, which are all these what we have here.
And the top mass is sorry.
Yes, the other uncertainties, the other theoretical ingredients are fixed. So in particular, the fine structure constant, of course, the Z boson mass is fixed. I think that the uncertainty would be small, but also the top mass is fixed and the Higgs mass is fixed. So this is basically just a propagation of the expected experimental uncertainties to the results. But yeah, you're right. Z mass contributes and the top mass would contribute also with some extent to this uncertainty. And also I must say, this is of course strongly scheme dependent. So here we expect the on-shell scheme where the Z mass and the W mass are the input parameters and GF is a prediction. Of course, if you would consider GF as an input parameter, then all this looks very much different.
Okay, thank you very much. So I don't see any more questions. So thank you very much, Daniel, again. And this is the end of, sorry, Uta, you wanted to add something?
Yeah. Because Daniel, you were, so sorry, Nancy, but you were just somehow the scheme dependent, but this is exactly one of the powers that if we can have this cross check of the various schemes among each other, to really see this big puzzle, if this is adding up as we think it should add up.
Yeah, I mean, from what we know from the global fits, that this fits all together, regardless what scheme you're using, in a sufficiently precise manner. But what I think is important is this K-dependence, because this K-dependence tests the gauge structure with high precision, and also basically it is sensitive to any deviation for different scale values. And if we can test up to the TeV regime with per mil precision, this I think would give more insights to what we have nowadays from this just from C-pole fits.
Very good.
Okay, thank you very much for the comment. Okay, so thanks again, Daniel, and I want to thank all the speakers for our session on behalf of all the organizers. Yeah, this is the end of our session, and also I would like to thank all the participants for attending until the end. So thank you very much, and see you soon. Bye bye.
Bye bye.
Yeah, thank you.
Bye.
Thank you.
Bye.
Bye bye.